Okay, great. Hi, my name's Richard Taylor. I'm standing in today because both Dick and Peter are out of town. And I'm losing my voice, so you're going to be lucky to finally hear this lecture, but we'll see what I can do. So they asked me to talk about the symmetric group, and in particular conjugacy classes in the symmetric group. And so I think you've already... Let me start by reminding you about the symmetric group. I think you know most of this. So, and tell me if I'm saying things that you are not familiar with. So, it's traditional to write Sn for the symmetric group on n letters. Which is the set of bijections from the set of n elements to itself. And traditionally you label those elements 1 to n. So the permutations or bijections, it seems to me the book you're using doesn't make a very good job of this. Most of the book writes functions acting on the left. And to meet other conventions, it suddenly changes that in this section on the symmetric group. So I'm going to do anyway. It seems to me silly to change in the middle of the book because it's just going to confuse people. But anyway, I'll do what the book does. So it's going to act, these permutations are going to act on the right. Which means I'm going to write P of I, as long as I remember to do this, rather than I of P. And this has the effect that if you first act on I by P and then on Q, it's the same as acting on I by the product PQ. What else should I remind you about? So then there are two notations for elements, for permutations or elements of the symmetric group. The first is simply to give a list of where all the elements go. So if I had an element of the symmetric group on 6 letters, which sent 1 to 3, I would write 1 underneath the 3 underneath the 1 to show that 1 goes to 3, and then we might have 2 to 6, 3 to 5, 4 to 4, 5 to 1, and 6 to 2. Okay, so this is the permutation that sends this row, element of this row to the element of that row. And I'm going to be using that a lot, so let me call that particular permutation P. And just to review how this works, let me have a second permutation Q, which will be 1, 2, 3, 4, 5, 6, 2, 1, 4, 5, 6, 3. And so if I'm interested in the product PQ, six, 5, 4, 1, 2 into 2, 1, 4, 5, 6, 3. So are you all familiar with how you would calculate a product like that? Somebody's shaking their head. So, sorry? Right. So what would happen to 1 because we're writing the action on the right, so if I look at 1, again, I'm just going to write where... Are you familiar with this notation for writing permutations as 2 rows in this way?
Actually, it's new for us.
Sorry?
It's sort of new for me anyway.
Oh, I see. Yeah, okay. So I had understood from what I had been told that you were familiar with this, so I'm sorry. Right, so it's just a way of writing what the permutation does. You just want to keep track of where every element goes. So in the first row, you write the elements that you're going to permute, this will be an element of the symmetric group on 6 letters. And on the second row, you write where they're going to go. So 1 goes to 3, 2 goes to 6, 3 goes to 5, 4 goes to 4, 5 goes to 1, 6 goes to 2. So if I want to figure out a product of two such things, what do I have to do? I have to figure out where 1 goes. So I have to figure out what's the image of 1 under the product PQ, which is the same as 1 acted on by P and then acted on by Q. So 1 under P goes to 3, and then under Q, 3 goes on to 4. So it's 1, 4. Similarly, 2 under P goes to 6, and then under Q, 6 goes on to 3. So I would write a 3 here. So does somebody want to tell me what I write underneath 3? 6. Thank you. 6. And 4 goes to 4, goes to 5. 5 goes to 1, goes to 2. 6 goes to 2, goes to 1. I haven't made a mistake. Okay, so this is one notation for permutations. Very straightforward. There's a second important notation, which is the cycle notation. So have you met the cycle notation to some? Yes. So for some reason they've talked about the cycle notation and not the easy one. Okay. So in the cycle notation, you somehow think more about what's actually happening. So you have the point 1, and let's look at the permutation P. What does P do to 1? 1 goes to 3. And then if you look at 3, 3 goes to 4. Sorry, I'm doing the wrong one. 3 goes to 5 under P. And 5 goes back to 1. So if you keep applying P, then 1's going to 3, goes to 5, goes to 1. It's just going to cycle round these 3 points. And if you look at, so what are we missing? We haven't got 2 yet. So if we have 2, what will happen to 2? 2 will go to 6, and then 6 will go back to 2. So we have 2 going to 6, and then that will go back to 2. So as you keep applying P, you're just going to keep cycling around these 2 points. And then finally, there's the point 4, which is just left fixed. It goes to itself when you apply P. And you record this in the so-called cycle notation. 1, you just write strings in parentheses for these cycles or the orbits that you get for P. So 1 goes to 3, goes to 5, goes back to 1. 2 goes to 6, goes back to 2. 4 stays where it is. Okay? So this is another, the so-called cycle notation for P, and there's a certain amount of ambiguity when you write this. Well, I mean, there's not a unique way of writing P in cycle notation. I can put the cycles in different orders, and I can, within each cycle, I can rearrange the order of the letters. So I could also write this as 5, 1, 3. I can cyclically permute these, because 5 goes to 1, goes to 3. Depends where in this triangle I start. If I have a 1 cycle, I can just drop it. Doesn't really make any difference. And it doesn't matter what order I write the cycles in. They don't involve any common numbers, so that this only moves 5, 1, and 3, and this only moves 2 and 6. So there's a certain amount of ambiguity. But that's the limit of the ambiguity. So the basic fact is that any permutation can be written uniquely as a product of disjoint cycles. Disjoint meaning they have no numbers in common, no number occurs in both cycles, disjoint cycles, up to the possibility, the various switches I explained you could make there, except you can reorder the cycles cyclically permute the elements in a cycle and you can drop one cycles. So, I mean, sometimes people would make the convention you always have to put them in, but it's just time-consuming to do that. Okay, so is this familiar to you from? Yes, good. And you can calculate products in this way. So in this notation, then Q would be, it would send 1 to 2, which goes back to 1, 3 to 4, 4 to 5, 5 goes on to 6, goes back to 3. So this is the cycle decomposition of Q. And you can calculate again the product PQ as, so it's 2, 6, 5, 1, 3 times 1, 2, 3, 4, 5, 6. So how do you work out the product when you work in cycle shapes? Was this something you've practiced doing?
Not a whole lot.
Not a whole lot. Okay. So, so for some reason let me correct this. Let me just use the original form I had for this thing. 1, 3, 5 doesn't matter. 2, 6. Okay, so I want to write it as a product of cycles. Well, I have to choose to start somewhere. It doesn't matter. Let me choose to start with 1. I want to find the cycle involving 1. So where does 1 go if I apply the product PQ? Well, I'm sort of acting from the right. So 1, first of all, goes to 3. I look along for a 1. I find it here. It moves to 3. I've now got a 3, and I look along to find anywhere else it might be and see where that moves from. The next time I find a 3 is here. It moves to a 4. Then I look along, and there are no more 4s. So it ends up at 4. Then I'm going to start with 4 and see where this moves to. So 4, I look along until I find a 4. The first place I find it is here. That 4 moves to a 5, and I don't see any more 5. So that will end up at 5. I then want to find out where 5 goes to, so I look along here. First place I find a 5 is here. Where does the 5 go? It's cycled back to 1. Okay, so now I've got a 1. I move along again to look for another 1. The next one is here that goes to a 2, and there are no more 2, so it ends up at 2. Now I want to ask, where does 2 go to? Okay, so I start with 2. What's the first thing that tells me to move a 2? It's this 2 cycle. It's going to move the 2 to the 6. I've now got a 6. Anything else going to move a 6? Here's a 6. It's going to be moved back to a 3. Nothing else will move a 3. So I get 3. So I'm always moving to the right and switching something every time that number occurs. So where have I got to? 3. I look along, the first 3 is here. This cycle will move it to a 5. I've now got a 5. Move along, the next place I see a 5 is here, which is moved to a 6. Left there. 6. Look along and First 6 I see is here, it's moved to a 2. Look along for a 2, there's a 2 here, it's moved to a 1. Look along, there are no more 1s, so that's a 1, and we already had a 1, so it's now going to cycle back on itself. So the product PQ is just 1 6 cycle, and with a bit of luck this agrees with what we had here. 1 to 4, 4 to 5, 5 to 2, to 2 to 3, 3 to 6, 6 to 1, so it does agree with what we did before. Okay, is that clear to everybody, or do you want me to do another one? Some people don't want me to do another one, some people aren't saying anything. Is that clear? Yeah, great. What's p to the 6, by the way? It's the identity, right. How did you see that?
There's an element of order 3, and an element of order 2, and an element of order 1. So if you raise it to the 6, then they all go to 1.
Yeah, that's right. These elements, it's a product of things that commute with each other, because disjoint cycles with no common element commute, as I explained here. I can reorder them. It doesn't matter whether I do the 2 to 6 first or the 5 to 1 first. These things commute because they've got no common element. And so if I raise it to the 6th power, it's like raising this to the 6th power, and this to the 6th power, and this to the 6th power. This is a 3 cycle, so when I do it 3 times, I get the identity. This is a 2 cycle, so when I do it twice, I get the identity. So when I do it 6 times, this is the identity, and this always was the identity. Or you can think sort of pictorially, as I do P, I move around this triangle. If I do it any multiple of 3 times, everything in this triangle will be fixed. If I do it any multiple of 2 times, everything here will be fixed. And this somehow illustrates the beauty of the cycle notation. You can very quickly see things like this. Whereas if I just wrote down, well, I've removed it, well, I wrote down Q equals this, and asked you what Q to the 4th was, and from this table it would be completely hopeless. I mean, you just have to do the calculation. But as soon as you've written it in this form, you immediately see that Q to the 4th is the identity, because it's the commuting product of a 2 cycle and a 4 cycle. Okay. Okay, well, the next thing I want to do is calculate the product Q inverse times P times Q. So let me write that. 1, 2, 3, 4, 5, 6. 2, 1, 4, 5, 6, 3. Inverse. I'm going to write this in this shape. I'm going to write P as a in the cycle shape, and then I'm going to write the Q again in this shape. 1, 2, 3, 4. I was told to quarter these boards. Well, maybe this will just fit. 2, 1, 4, 5, 6, 3. And I want to express the answer as a cycle. Let me start the first cycle with the element 2. Can anybody tell me what 2...
You want to reverse to get the inverse conjugation?
Well, I want to calculate this. Under this whole product, what's 2 going to go to? 4. So 2... I've got to do the inverse of this permutation. Where's 2 going to go to? Well, I look for 2 in the bottom row and look up above it. What mapped to 2? It was 1. So 2 goes to 1, 1 goes to 3, and then 3 goes to 4. Excuse me. Where am I? Okay, 4. Where does 4 go to? Well, 4 came from 3, goes to 5, which goes to 6. and 6 came from 5, which goes to 1, goes to 1, which goes to 2. So it cycles back to 2. And then let me put a 1 here. 1 came from 2, goes to 6, goes to 3, and 3 came from 6, goes to 2, goes to 1. So that closes, and we're left with a 5. 5 came from 4, stays where it is, goes back to 5. Can anybody tell me simply what's happened when I've done this? Yeah, but how could I have seen these numbers almost at a glance without doing the computation I just went through? Can anybody see? That's right. So first of all, you should notice the cycle shape is the same. By the cycle shape, I mean the number of cycles and their length. We've got a 3-cycle, a 2-cycle, and a 1-cycle. So the cycle shape has been unchanged. And in place of the 1, 3, 5, what do I have here? Well, 2, 4, 6, but what? Sorry? The Q image of those. 2 is just the Q of 1. 4 is just the Q of 3. And 6 is just the Q of 5. So this was Q of 1, Q of 3, Q of 5, Q of 2, Q of 6, Q of 4. So when you form the conjugate Q inverse PQ, and you're working in cycle shape, it's very easy what you do. You just take the original cycles and replace every time you have an integer here, you just replace it with Q of that integer. So let me, in case that's not obvious, let me explain slightly more carefully why that's true. So the key point is the following formula. Suppose I is sent by P to J. And now what are we interested in? We're interested in I, where I acted on by Q is going to be sent by the product Q inverse PQ. Well, what is this product? The Q and the Q inverse cancel, so I just can, and changing the order of the parentheses, this is I acted on by P, acted on by Q. So I acted on by Q is sent by this conjugate of P to the image under Q of I acted on by P. Okay? And so if I have a cycle, so if P, so P is the form I1, I2, IR, I1 primed up to IS primed, and then some more cycles, then this Q inverse PQ, what's the cycle shape of Q inverse PQ? Sorry?
I1Q, I2Q.
That's right. So if I look at I1Q, let's start the first cycle with I1Q. Where's I1Q going to be sent by this? Well, it's going to be sent to I1P, which is just I2, acted on by Q. Where's I2Q going to be sent to? Well, I2Q is going to be sent by this to I2P, which is just I3, acted on by Q. up to IR acted on by Q. Where's IRQ going to be sent? IRQ is going to be sent by this to IRP, which is just I1 acted on by Q, which was the first element of this cycle. Then we're going to get I1 primed Q. Let's start the next cycle with that. Where's this going to be sent? I1 prime Q is sent by this to I1 primed P, which is I2 primed, acted on by Q. Okay, so this is just what we observed in this case, that when we conjugate by permutation Q, what happens to the cycle shape is that we replace every element in the cycle by its image under Q.
Sir?
Okay, yes?
Where you've written Q1, Q3,
I've moved it onto the wrong side, haven't I? My apologies. Thank you very much. 1Q, 3Q, 5Q, 2Q, 6Q, 4Q. Thank you. Okay, are there any questions about that? Okay, so let me formalize that as well. Write it down. So, first of all, two permutations which are conjugate in Sn the usual words people use are have the same cycle shape. So I mentioned it briefly, but I haven't really said what I mean by cycle shape. So by cycle shape, I mean when you express them as a product of disjoint cycles, you have the same number of cycles of each length. So i.e. when expressed as a product of disjoint cycles, they have the same number of cycles of every length. So this and this have the same cycle shape. They have one cycle of length 3, one cycle of length 2, and one cycle of length 1. Okay, and sort of that's now obvious from this calculation. I mean, we've taken the cycle shape for P and we've obtained the same one for Q inverse PQ. And the converse is also true. So conversely, where are we? Two permutations. If two permutations have the same cycle shape, they are conjugate. So the second, I'll justify this in a moment, but the second thing that the cycle notation is very good for is that it very quickly allows you to understand conjugacy in the symmetric group, and in general understanding conjugacy in a group is one of the most important things to be able to do. Okay, well, let me justify this second assertion by just doing an example, and I think it will be immediately clear why that's true in general. So let me again look at my example. This, and I want to write down something with the same cycle shape. This has the same cycle shape, so this proposition is telling me I can write this as a conjugate of this for some q. Well, what q should I take? Let's have somebody outside the front row answer. One to 6, 3 to 5, yes, right, 5 to 4. Okay, so we know that this will just be q of 1, q of 3, q of 5, and we want that to be the cycle 6, 5, 4. So we better send, well, we've got some choice. We could send 1 to 5, 3 to 4, and 5 to 6, but the obvious choice, the way I've written it, is just to send 1 to 6, 3 to 5, 5 to 4, 2 to 3, 6 to 2, and 4 to 1. And I hope it's sort of obvious that that construction will work whenever I write down 2. In any symmetric group, whenever I write down two products of disjoint cycles with the same cycle shape, I can always, just by doing this, find a permutation that will conjugate one to the other. Okay?
So the number of ways is the product of the orders of the cycles, right?
If all the cycles are different lengths, so if I had 2 cycles of the same length, there would be some ambiguity about which of those cycles I was going to. Do you see what I'm saying, or you want me to?
No, I think it's.
You see what I'm saying? You could write down a formula for. It's an interesting question, so let me spend a moment. So if I looked at the cycle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I asked how many ways how many q, so I want the number of the set of q such that q inverse this q would equal, so q in S12, such that this is equal to, well, I can even write the same one again. It doesn't matter. Anything with the same shape would do. So can you see what the answer to this is?
Yeah, because if we.
Let him have a moment to see. So I've got to match this 2 cycle with one of these 3 2 cycles. So how many choices do I have there? So I have 3 choices. When I do that, how many ways are the matching of these 2 cycles together? 2. I can either send 1 to 5 and 2 to 6, or I can send 1 to 6 and 2 to 5. Okay, assume that I've chosen the way to match these 2. How many 2 cycles could I match this one with? 2. And when I do that, how many ways are there of actually doing that matching? 2. And then with the final 2 cycle, how many ones can I match it with? 1. And there are 2 ways of doing it. Okay, and then let's look at the 3 cycles. How many ways of matching? How many 3 cycles could I match this with? 2. And how many ways, if I choose to match it with this one, how many ways of matching it are there? No. How many ways of matching it are there? 3. I can send I asked where the 7 goes. It can go to the 10 or 11 or 12. Let's suppose I send the 7 to the 10. Where does the 8 have to go? To the 11, and the 9 has to go to... So once you've fixed where in this cycle you're sending the first element, everything else is fixed because it has to be a cyclic permutation. So there are just 3 ways of matching these 2 cycles. And then this 3 cycle has to go to here, and again there are 3 ways of matching it. So I could write this as 3 factorial times 2 to the 3 times 2 factorial times 3 squared. Okay? And in general, I mean, if I had... well, actually, let me not write it. Let me just tell you the answer. If you would take if there are A11 cycles, you would take... So if P has A11 cycles, A2 2 cycles, and so on, then how many Q satisfy a Q inverse PQ equals P or any conjugate of P. It doesn't matter what I put there. Well, can anybody tell me what the answer is going to be? Sorry, say that again.
The product of AI factorial.
That's right. So the number of ways of matching up all the 1 cycles is all the I cycles is AI factorial, and for each such matching, I can actually match the individual cycles each in I ways. So I get the product over I. Well, it'll stop eventually. But so this is the answer. Okay. Fun question. Now let me see. Okay, well, let me... Let me actually do a similar exercise. So let me look at the symmetric group on 5 letters. How many elements does this have? Sorry? 5 factorial order, so order 120. So how many conjugacy classes does it have? Can somebody tell me, can somebody list the conjugacy classes? Sorry? Give me some representatives of the conjugacy classes. Well, yeah, okay. You can do them in any order. 1, 2, 3, 4, 5, a 5 cycle.
4 cycle.
1, 2, 3, 4. Yep.
3 cycle. 3 cycle with 2 cycles.
Yep.
2 cycle. 2 cycle. 2 cycle.
Have we got them all? Probably got them all. Yeah, I think we've got them all. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right, so if you want to list the conjugacy classes, you just have to list elements of all the possible cycle shapes, because we know that conjugacy is equivalent to the same cycle shape. So we could have all 1 cycles, as it were. Or we could have one 5 cycle, we could have a 4 cycle and a 1 cycle. If we could have a 3 cycle, and then we could either have 2 1 cycles or a 2 cycle. We could have a 2 cycle and then either a 3 cycle, but we've already had that, or another 2 cycle and a 1 cycle, or just a 2 cycle and then 3 1 cycles, as it were. And there are no other possibilities. How many elements are there in this conjugacy class? 1. The only conjugate of the identity is 1. How many 5 cycles are there in the symmetric group with 5 elements? No. How many ways can I write down a 5 cycle like this? How many choices are there for the first element? 4 factorial, that's right. 4 factorial is what? In a minute. Am I right? Yes, it's 4 factorial, yes. Sorry. 4 factorial is 24. Why? Well, I can choose this element in 5 ways. This is then in 4, this then in 3, this then in 2, this then in 1, but which looks like 5 factorial. So it's 5 times 4 times 3 times 2 times 1. However, this is the same as the cycle 2, 3, 4, 5, 1, which is the same as the cycle 3, 4, 5, 1, 2, which is the same as the cycle 5, 4, 5, 1, 2, 3. It's the same as the cycle 5, 1, 2, 3, 4. So this same cycle can be written in 5 different ways, depending which of these elements I choose to put first. So I have to divide this answer by 5, which is why I get 4 factorial. How many 4 cycles are there?
30?
You could well be right. So how did you get that?
I did 5 choose 4. Because you get to pick the first 4 elements out of the 5 in the 4 cycle.
Okay. And then multiply by sort of 4 factorial divided by 4, which was 3 factorial. Yes. Okay. Let me write it a different way. I mean, that's fine. Sorry.
You could say for the first cycle you choose in 3 factorial, and then the 1 cycle you can choose in 5 ways. So it's more.
Yes, if you like. You first of all choose this in any of 5 ways, and then how many ways of when you've got 4 elements left, how many ways are there left making that thing? That's true too. I mean, yeah, these are all perfectly good and equivalent ways. The way I would say it is we want to write it like this. So I can choose this in 5 ways. I can choose this in 4 ways, this in 3 ways, this in 2 ways. Didn't matter, but then that gives me this 4 cycle, but there are 4 different ways of writing this 4 cycle, so I have to divide it by 4, and then there's just a 1 here, which is again 30. What about this? Sorry? What did you say? Sorry?
I learned at 50. I hope I won't regret it.
50, 50. Yeah, no, I don't. You'll regret it. Sorry? Well, let me do it again. This one you can choose in 5 ways. This one you can choose in 4 ways. This one you can choose in 3 ways. Divide by 3 because I can write this given 3 cycle in 3 different ways. Then it really doesn't. I don't have any other choices because the others all have to be 1 cycles. I could write times 2 times 1 divided by 2 because it doesn't matter which order these are. But anyway, you get this, which is 20. This one is, so you can choose this in 5 ways, this in 4 ways, this in 3 ways. Divide by 3 because it's a 3 cycle and the order doesn't matter. The remaining elements I've now got, this can be chosen in 2 ways, and then this is fixed. It doesn't matter what order I wrote them in, so I divide by 2. So it's probably 20 again. This one I can choose this in 5 ways, this in 4 ways. it doesn't matter what order I chose them in, so divide by 2. I can then choose this in 3 ways and this in 2 ways. It doesn't matter what order I chose those two in, so I can divide by 2. But it also does. But it's also true that 3, 4 is the same as 1, 2. I mean, I could also write this as 3, 4, 1, 2. I could put the 3, 4 here and the 1, 2 here. So it doesn't matter what order those two are in, so I divide by another 2. Then you're left with 1, so that's 15. And in this one, I can choose the 1 in 5 ways, the 2 in 4 ways. When I've done that, it doesn't matter the order, so I divide by 2. And then these are all going to be 1 cycle, so there's no choices left, so that's 10, I think. And with a bit of luck, these things will add up to 120, 25, 55, 75, 95, 110, 120. So indeed, they do add up to 120, so we haven't made a mistake, which is rather lucky. Okay, so reasonably clear to people how you can count these sorts of things. You have to think a bit carefully exactly, because the problem is there's a certain amount of ambiguity, and you have to remember exactly what ambiguity there is. So it's very like this formula I wrote down here. If you try to write it you write it as a product of cycles. You basically have a 5 factorial to begin with, which is the ways you can choose these things, and then you've got to divide by any ambiguity. So whenever you have an n cycle or an r cycle, you divide by r, because you can write them in any order. And whenever you have a pair of cycles the same length, you divide by another 2, or if you had 3 cycles the same length, you would divide by a 3 factorial, or 4 cycles the same length, you would divide by a 4 factorial, because it didn't matter what. So in fact, the formula is in Sn, so the order of the conjugacy class of P I mean, I don't really expect you to remember this formula. It's just, seeing as you persuaded me to do this calculation, I might as well write it down. The important thing is the sort of thought process that goes into working it out. It's just n factorial divided by this thing. If P has these cycles of these shapes. But as I say, you don't want to remember this formula, you just want to remember the thought process that goes into it. Okay, so I've run out of time. At the end of the section I was supposed to tell you about, there is which is section whatever it was of the book, 6.6. There's a rather specific little calculation which I guess was put there because he's going to use it sometime later, which I don't now have time to talk about, but you should read about it. Concerns the case of the symmetric group. So if on a prime number of elements, so if P is a prime, well, so we're going to consider SP. The order of SP is P factorial. What power of P divides this? Just 1. Can somebody give me a Syloff P subgroup? You talked about Syloff subgroups. Yeah. Of SP. Sorry? Well, it's going to be big. What's the order of the Syloff P subgroup going to be?
So I was thinking the P elements that you had if you divide, but I can see now that maybe that's a little bit muddled.
So can you think of an element of order? So anything in the Syloff is going to have order P. Can you give me an element of order P?
The elements that are
A cycle of length P is the cyclic group generated by any element of order P. That will be a subgroup of order P, so generated by 1, 2, 3 up to P. The cycle. Okay, and then the exercise concerns Syloff P subgroup. Let me write P A CIL of P subgroup P of SP is the cyclic group generated by this, the normalizer in SP of this cyclic group P, that's the set of all elements which, do you know what normalizers are? Yeah. So the question is to calculate the normalizer of this CIL of P subgroup. As I don't have time to talk about it, I'll leave you to read about it at the end of section 6.6. Or you could almost try it as an exercise. It's actually going to have order P minus 1 times P. First of all, you take something in the normalizer, you get it to fix 1, and then you ask what it has to do. Okay, I'll stop there.